this expression looks horrible. A bit like my shirt. It looks horrible, but it is actually okay once you get used to it. So what we've got here is things like p of 0. So I'm going to start on the inside and work outwards. So if we sub x equals 0 into these expressions, we'll find out what p of 0 is. Well, that's 0 plus 1, which is 1. Find out what m of 0 is. And then we're going to have to think a bit about where we're going to use all of that. But those are some good starting points. I like having these kind of basic starting points to start with, to work towards more complicated things. Okay, so I'm following what Josh has put in chat. P of 0 is 1, so this bit is 1. M of 0 is minus 1. M of 0 is going to be minus 2. Okay, so this is my first S thing. I've got S of 1, minus 1, minus 2. And then we've got, this one is going to be, okay, let's put the S in there as well. S of 1, this is minus 1, plus of 0. Oh, sorry, last time someone helpfully pointed out that P probably stands for plus and M probably stands for minus. So I'm going to say that throughout. And then this term is like S of minus 1, plus of 0, minus of plus of 0 is 0, right? Okay. Yeah, here's a great comment. Okay, so someone in chat has just said, you do not need to evaluate all of the expressions. Once you know the first part, that'll tell you that you can ignore one of the other parts. The person here has cleverly realised that this function says, look, if x is negative, in this case, if x is negative or 0, then this s function just returns y, and you can ignore z. Whereas if x is positive, then this s thing takes the value of z, and you can ignore y. Okay, so this is pretty good. This lets us ignore some of the inputs. Okay, so it's a great shortcut. My strategy of building up from the inside means that I'm evaluating a lot of this stuff, and someone in chat has realised that if you think about it from the outside inwards, then you have this insight that some of it doesn't matter. Okay, still got to evaluate some of these things, right? So this big S on the outside, as I'm evaluating that, I really care about this first term, because the first term will let me know whether I can ignore the second one or the third one. And I'd like to do less work. So let's look at this. So this S of 1, minus 1, minus 2. Well, here x is positive, so this takes the value of the third input, z. So this thing is minus 2. Okay, so I've got these two things as well. Okay, I've got this big S on the outside. Let's copy all my line down, so it's really clear what I'm doing. S of minus 2, and then I'm going to need this one as well. Okay, this first thing is negative, so we care about the middle argument, but we don't care about this. I'm going to write whatever over here. We don't care what that one is. We do care what this middle argument is. S of 1, minus 1, 2. Well, 1 is bigger than 0, so this takes the last argument from this one. That's 2. And now we've got S of minus 2, 2, whatever. And I've written whatever because this minus 2 means we're going to take this second. We're going to take this middle input and ignore the z. Okay, so this is 2. Here's on screen some awful definition of f, and I say awful because at first sight it's not so bad, right? It's like these other functions we had. It's got 2 inputs, okay, and some definition on the right, but then you notice that it's got an f in here. So this is kind of defined recursively. The value of the function depends on the value of the function at a and b minus 1, I guess, for m of b, which is a bit awkward. Okay, so we're faced with, as is often the case in maths problems, we're faced with an object. I've got really no idea how to get started with this, and it's up to you, in this case maybe me, to come up with a way to get started. Yeah, okay, here's a good starting point. So Mimi says we need to look at Z since it's positive, which I think means, right, okay, so we're trying to work out f of 5, 2. And Mimi's correctly noticed that 5 is positive. Oh no, 2 is positive, sorry. B is positive. I mean, they're both positive, but relevant fact, B is positive. That means that we're looking at this case where the first argument going into this big S is positive. So we do need to look at Z. Okay, so f of 5, 2 is going to be equal to, just knowing that B is positive here, 2 is positive, is going to be equal to P of f of, and then A is 5 and M of B is 1. I think, okay? Taking this, because B is positive, this S switch function thing says, well, first argument is positive, so we're going to pull out this stuff. And then I've written in what the values of A, I guess I worked out M of B in here. So I guess this recursion, just fiddling around with what do I know from here, so this is P means add 1, so this is 1 more than f of 5, 1. Of course that's not super helpful, but I can do this again. 1 is also bigger than 0, so this is P of f of 5, 0. Okay, I think that's the right number of brackets. Where am I going with this? Well, it sort of works down to 5, 0. 0 is interesting because it's in a different case for this switcher. This says, aha, when you get down to a 0 here for B, well, this switcher function notices that your first argument is less than or equal to 0. So now it's going to pull out the first argument. We're getting somewhere because we can do f of 5, 0, right? F of 5, 0, well now, this is going to be S of 0, P of A is 6, and then I don't care what this is, because when you put 0 in the first argument of the S function, you just get this thing out here. You just get the second argument out. This is just 6. Okay, that's like a concrete number that's come out. Okay, don't get too excited. We've got this thing is equal to 6, because finally when we get down to 0 here, this kind of stops being a recursion relation, because when you get down to 0, the switcher kind of says, well, actually, don't look at the bit with f in, look at this nice other bit of function, where it's just 1 more than a. Okay, spit that out. It starts spitting out y instead of z. Okay, so that is 6. And then I think putting all that together means that this is plus of 6. So I think this is 8. Part 3 is kind of testing whether we can do this previous part of the question sort of in general, to do this thing for a general A and B. Have we understood what was happening each time we plugged in A and B there? And the pattern of what's going on, I suppose, is that while B is positive, we can use this recursion relation to relate f of A and B to f of A and then 1 less than B. It feels like something we can do. Until we get down to a statement like this, with the same A but a 0 in there. Let's try and write down some true statements, because that's kind of, I'm trying to vocalise my kind of intuition or feeling for how this is going to work. What I'd actually write down is something like, I don't know if 0 is positive or not, but I'd write this down anyway. I'd write down f of A 0 is equal to S of, and then this B is 0, P of A, P of F of loads of horrible stuff, M of B, whatever, all this stuff. But because we're in this case, where the first argument to S is less than or equal to 0, this is going to just pull out the second term, P of A. So this is just going to be equal to P of A, which is, A plus 1, which is pretty nice. Okay, that's true for all A, and for B 0 at the moment. For other B's, for B bigger than 0, I'd say that f of AB is equal to, well, now we're in this case where the argument is bigger than 0, so this is going to pull out the second thing from this expression, and it's going to say add 1 to this thing to add 1 to the value of the function evaluated with the same a, but 1 less b. Okay, I think that means, so spotting a pattern here, I can keep doing this. Okay, so that's going to be, let's rewrite this slightly. Let's say this is f of a b minus 1 plus 1. Okay, ooh, running out of space. Okay, so if we keep doing that, then we keep going down on the argument inside, and we keep going up over here. So that f is going to relate to the previous value of f, previous in the sense of b, 1 less b. Keep going down until you get down to f of a0. And f of a0 was a plus 1. And I think, chasing through all of the plus signs and watching out for everything that goes on in there, I think f of ab works out as being equal to a plus b plus 1. Yeah, here's a great question. So for the last part, it says you can only use P, M, and S. You can use A and B as well. If your answer probably has to depend on A and B. They mean that you can't use, and this took me a while to realise, you can't use plus and minus, or times or something. Your answer can't just be A plus B. Because that works. That is a function that returns a plus b. Or you can't write b plus a. That's a function that returns a plus b, but it uses this plus operation as well. They want us to just use p, m, and s. The way I approached this, I think, was to start by trying to work out what I wanted to happen in different cases. There's kind of two cases going on in this previous definition. We've got this thing, I guess because of the nature of the switcher function thing, that you can make it do two different things, and you get quite a bit of control about when it's doing this and when it's doing this, whatever these things are. So I had to think a little bit about what I wanted it to do in different cases. I'm being a bit obscure, but I'll try and get more precise. And I guess because I want to use this idea from the previous part of the question, this thing about f, I really like the way it relates to the function to other values of other values of the function. That feels powerful. So I think we're going to write down a function that looks a bit like, here's my kind of scribbled working. It's going to be s of switcher thing, and then what I want it to do in cases where this is negative or equal to 0, and then stuff I wanted to do where my switcher function is 0. Is 0 or bigger than 0, I guess. Sorry, is strictly bigger than 0. Yeah. You know what I mean. Switcher that does this is going to have a form a bit like this. And I can see in chat, people are suggesting that this first thing here should be something like B. So I guess people are imagining that, I suppose what I want is something like, I'm going to swerve this towards how I did this, which is think, if B is actually if B is actually negative, strictly less than 0, then relate to g of a b plus 1. This is my plan. But if b is actually negative, then try and move towards 0. Relate it to what I want, what's going on at g of a b plus 1. Try and get back to 0. Because at 0, if b is actually equal to 0, then I know what I want. Then I want to return just a, I think. I want to return just a if b is equal to the number 0. So I'm kind of inspired by this previous part of the question, right, where we had this thing that says if b is positive, then this thing does a lot of work to return something related to previous values of the function. And if b is actually equal to 0, then this pulls out p of a, something nice. Okay. We've got these kind of different. This is my idea for different cases. How do I actually write that down? So it's slightly awkward because less than 0 is not quite how this switcher works, and I can see in chat people have got different workarounds for how to get around that. here's how I got around this. I thought if b equals 0, then I want to be in the big case. I want to be in the case just getting through into this case where x is nice and big. Annoyingly, x equals 0 doesn't actually get me into that case, but b plus 1 would be. b plus 1 would be just into like the right range of switching values. Yeah, Phil says I'm not allowed to use b plus 1. I'm not allowed to use b plus 1. This is not allowed. This is rough work still. We're getting there. Okay, I'm not allowed to use b plus 1. So b plus 1 does the right kind of switching behaviour for me, because when b is strictly less than 0, this thing is less than or equal to 0. And when b is actually equal to 0, this thing is 1, which is strictly bigger than 0. Hooray, okay. Still got to untangle this a bit. If b equals 0, then this is positive. It's going to pull out this term. And I just want it to return a. So I think I can put a here. And in this case, I want, what do I want? I want g of a, b plus 1. I want it to be related to this, but subtract 1. Okay, that's my plan. I have this switcher function that either pulls out this value when b is equal to 0, or when b is negative, less than 0. This thing is 0 or less, so it pulls out this madness, which relates it to the value when b was 1 bigger. Okay, so my plan is to define this when b is 0, and then let the other ones relate back to ones with b equal to 0. Okay, I need to tidy this up by replacing the plus 1s with p and the minus 1s with m, which makes this look a little bit more complicated, but morally I think this is the same. Plus of b for b plus 1, and then I want g of a, m of b, but then I want to subtract 1. No, that's a p. Then I want m of this to subtract 1 off the end. A. That's my answer anyway. Okay. Part 1. Show there's no date with no repetition of digits in the years from 2000 to 2099. Okay, and people in chat seem to have told me that all of these years involve a 2, because there's a 2 at the start, and a 0, because they all start 2-0 in the years. Most months are less than 10, so they start 0, 0, 1, 0, 2, 0, 3. But 0 has already been used in all of these years in the Y2 slot. So that rules out a lot of months that it could be. Then there's a few months, November and December, that start with 1. December is out because it's got a 2 in the second place here. All of these years have a 2 in. And November is out because they're both 1s. So a repeated digit within the month there. Part 2 wants to know what the last date before today was with no repetition of digits. And I guess the first challenge is to find a year that doesn't have repetitions of digits in, because as you go backwards through the years, you find, well, 2010 had 2 zeros in it, 2009 back to 2001, actually 2000 I guess, those have all got loads of zeros in, so they've got a repeated digit just within the years. And then actually 1990s are all rubbish as well, because they've got 2 9s in, all the way back to 1990. And then actually 1989 is bad because it's got 2 9s in, and 1988 is bad because it's got 2 8s in. The first year going backwards is 1987. 1987 maybe, because we still need to find a day within 1987. Now within 1987 we've got to find a month. We've used 1 already, so we can't use December or November because they would put a 1 in this place. Okay, and I can't use the 10th. I can't use October either because it's got a 1 here. Okay, so I can't have, and then working backwards, I can't have 09 September because I've used a 9. I can't have 08. I could have 06 here. I guess we're working backwards through the year to work out what we could have. And then, well, I haven't really got many numbers left. I want this to be a big number. The biggest I can make it is not the 30th of June, because I've already used a 0 and won it out. Not the 30th of June, but maybe the 20-somethingth of June, and then the 20-somethingth of June. I would then think, hang on, I haven't used, the biggest number I haven't used yet, 9876, is 5. So I'd work backwards like that to get, I've got 25th of June 1987 as well. Okay, so part 3 of the question asks us, when will the next such date be? And wants us to explain our answer. This question was set in 2010, but actually it's going to keep working way past 2099 and still be the same answer. Okay, so the 2100s are also out. We saw that we saw that this century is out. The 2100s are also not okay, because they all have a 1 and a 2 in them in the year, right? And all of the months either have a 0, a 1, or a 2 in the first place or in the second place. That's kind of what we saw in the first part of the question. And if it's not using a 1 or a 2, it must be using a 0. And once we've used 0, 1, or 2, then we don't have any options left for the date in the month for D1 and D2 if we rule out all of the small numbers. Okay, so sort of chasing through all the possibilities for what the month is. If you were going to rule out 2 and 1, you end up with no dates left in there as well. The 2200s are obviously not okay because they've got 2 2s in them. But then the 2300s maybe work. Maybe we should look in 2300. The first interesting year in 2300 is I suppose 2301 technically has all its digits different, but there's this problem that it rules out 0, 1, and 2. And we'll do this little exercise before to say, oh, if you've ruled out 0, 1, and 2, then you can't write down a day and a month. You always use one of those when you write down DDMM. Okay, so in fact, I don't want to use 0s or 1s here either. And I can't use 2s and 3s because I've already written those at the start of the year. So this turns out to be not okay. We need to go to 2, 3, and then I need to write down the smallest year that doesn't use the numbers 0, 1, 2, or 3, which is 2345. Okay, and this is good because I've left over 0 and 1, so maybe I can write down a month and a date of the month using my 0 and 1 where I need to. I mean, it's not going to be November. November uses up 2 1s. It's never going to be November as a repeated digit inside just November. Okay. So let's work forwards, I guess. We want the next date, so we want to be as early in the year as possible. I want the month to be as small as possible. There's a bit of a trap, like I could try January. Let's go over here. Try January, but no, I've used 0, 1, and 2 again, and now I don't have any dates of the month left, right? Because I've used all the small numbers, so my day of the month would have to be like the 67th of January. That's terrible. Hasn't worked at all. January doesn't have enough dating. Okay. And in fact, then I can't use 2, 3, 4, or 5. So my next best bet is June in 2345. I can't use 2, 3, 4, or 5. And actually, it turns out there is a day in here because I've still got a 1 and a 7 are the smallest 2 numbers left over. So I could have the 17th. I'm using the smallest numbers available to me at the moment to build the 17th of June, 2, 3, 4, 5. That's the next date that doesn't have any repeats in its digits. For the last part, we're interested in the years starting with 19. So our day, month, year is supposed to look like this. So crucially, we've already used 1 and we've already used 9. We want no repeated digits. Okay, so a strategy that I've seen people in chat use is to think first about these digits here, the month digits and the first digit of the day. You see, we've already used 1, so I mean that rules out quite a few months. This is not 10 or 11 or 12 for the month. because we've already used the 1. So in fact it must be one of the months that starts with 0. Okay, so this is kind of step 1, M1 equals 0, because it's not 1. Okay, don't know what this is. This is some small number. I mean, it's not 9, but it could be something else. Okay, we'll get there. Anything else gives us a sensible month, so that seems nice. Step 2 seems to be to think, well, we're ruling out small numbers, 0 and 1. We saw in some previous parts that ruling out small numbers is dangerous because you run out of days. You see this dates number here, D1. It can't be 0 or 1 anymore. It could be 2 or 3, I suppose. But if D1 is 3, this has come up before. If D1 is 3, then D2 has to be 0 or 1 because of how dates of months work. There's only ever 30 or 31 days in a month. So D2 would have to be 0 or 1, but it's not. We've already used 0 or 1. So D1's not 3. This is not okay. D1's not 3. It's also not 0 or 1. So D1 is equal to 2. Okay, going pretty well. What have we got left? Well, we've got 4 slots and we've got 6 available digits. We've got the digits we've got 3, we've got the digit 4, we've got 5, we've got 6, we've got 7, we've got 8, we've got 6 possible digits, and we've got 4 slots. So the way people are phrasing this in chat is kind of a classic combinatorics thing. We want to pick 4 of these 6 things, and the order matters because different orders gives us different dates. So the thing you do is you have 6 choices for this first slot, 6 choices for the first slot, 6 choices for the first slot, and then you've used one of your numbers now, so you've only got 5 choices for this one. All your choices are independent, and you've got 4 choices over here, and then 3 choices over here. I think, does that work? 20, I can have any digit in here, those will all be nice. I can have any digit in here, those will all be good to me. I can have any digits in here, and those will be some year in the 1900s. 6 times 5 times 4 times 3 is 20, 60 is 360, which I've seen some people in chat get as well. So that's nice. So I tried plugging in small values to see what would happen. I feel like I've said that for every question today, but plugging in small values, I wanted to see what would happen when, when like x is 0, x is 1, x is 2, 2 to the x, floor of x or brackety x thing is 2 to the 0 is 1, 2 to the x floor is 2 to the 1 is 2. When this happens, this is 4, I think. And my kind of feeling is that like 2 to the x goes up like this, and then this floor thing is going to come in and round all those numbers down so that it will be 1 for a bit, and then it will be 2. We've seen that after 1, after x equals 1, this is x. After x is 1, this goes up to the number 2, and then at some point it's going to jump up to 3, I think, and then 4, and then 5, and we want to find this area underneath. This area made of those red rectangles. Okay, so a kind of crucial question, I suppose, is when is it doing this jumping? When does it jump up from, here the value is 2, when does it jump up to 3? We know that it's 4 when x is 2, so it's somewhere in between 1 and 2, it jumps up to the value of 3. This is the key to understanding this question, I think, is to find out where is this point on the curve, where floor of 2 to the x is 3 for the first time. And it's 3 for the first time when you round down that number, but you're rounding down just slightly more than 3, or rounding down 3 to 3. So it's equal to 3 for the first time when 2 to the x is actually equal to 3, which is when x is log base 2 of 3. Okay, so that's the answer for what is this number here. So it's log base 2 of 3. Because that's just the right number, so that when you plug it in, you get 3, and then you round down, and you're still at 3. Okay. So there's lots to do in here because we've got to work out, we've got to understand what's happening when we get all the way up to n. So when we hit n is a natural number, a whole number. I guess positive integer is what people sometimes say. This graph is going to be a bit awkward. But the value up here is going to be 2 to the n. Because when n is a natural number, so 2 to the n is also a natural number, so when I round it down, I'll get a natural number. Okay, and the curve has kind of been, I kind of want to draw this top part of the curve. This top part of the curve. It's just gone through n, 2 to the n. That's terrible, I'm going to have another go at some of that, but talk over the top. I'm kind of interested in what's going on near n. Has it been 2 to the n for very long, or just sort of a little bit? Can I understand where it's equal to 2 to the n? Right, now here's a nice line, there we go. N, okay. And after thinking about this for ages, I thought the thing is, I'd like to understand when is this equal to 2 to the n minus 1. So remember, the curve's getting rounded down. So it's just made it up to the value of 2 to the n, which gets rounded to 2 to the n. But just before, it was getting rounded to 2 to the n minus 1. The largest integer, less than or equal to x, was the previous integer, 2 to the n minus 1. And that was true between this point here and n. And after thinking about this for quite a long time, I realised that this is probably log base 2 of 2 to the n minus 1. So I had to do quite a lot of thinking and maths to work out what this value of x was. And it's just the right value of x, so that when I do 2 to the x, I get to 2 to the n minus 1. Okay, where's this going? Well, I've got this plan now that if I understand where all these rectangles are, I can write my area as the sum of all of those rectangles. Sum of the areas of those rectangles, okay. Put some more numbers in there. So what does that look like? That looks like, slightly over time, sorry. That looks like, so this first rectangle has got size 1 minus 0 times 1. And then the next one has got size log 2, 3 minus 1. That's its width. And its height is 2. The next one has got log 2 of 4, which is equal to 2, minus log 2, 3 times 3, plus so on and so on and so on, plus the last thing in here is log 2, 2 to the n, that's n, minus log 2, 2 to the n minus 1, that's the width of this last rectangle, and the height of that rectangle is 2 to the n minus 1. Okay, so I just need to add up all these terms, and then I'm good. And by adding up all of these terms is actually not that bad because there's lots of cancellation. You see I've got terms in here like in the log base 2 of 3 term. This appears here and here. Here there's 2 lots of it, and here there's minus 3 lots of it. And something similar happens for everything else, so that I end up with a whole bunch of cancellation. So maths that's easier to do on paper, check this for yourself, is that you can do a whole load of cancellation to get that this is minus 1 minus log base 2 of 3 minus log base 2 of 4 minus dot 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 minus log base 2 of 2 to the n minus 1 plus 2 to the n minus 1 log 2 to the n. Okay, simplify a little bit. This is 2 to the n. The only thing that doesn't have a minus sign is this 2 to the n log base 2 of 2 to the n. I'm going to write that as n again. Minus, and then there's a whole bunch of things. Log 2 times 3 times 4. I'm going to bring all the logs together, times all the way up to the last thing with a minus sign in it is this thing. There's this minus sign here. Okay, that is precisely option B.